All right. Today, we're going on a pretty wild journey, right down to the very bedrock of reality, to the foundations of mathematics itself. We're going to tackle a question that has kept the greatest minds busy for centuries.
So let's just jump right in. Think about this for a second. You've got some mathematical theorem, something you know is true. What's the absolute bare-bones, rock-bottom set of rules you need to actually prove it? That's the huge question we're digging into today. And here's the game plan. We'll start with the old-school search for mathematical truth, then check out a really clever modern twist called reverse mathematics. From there, we'll zoom in on a special area called the bounded approach, see how it links up with one of the biggest mysteries in computer science, and finally, wrap our heads around what this all means for the future.
Okay, so first, a little history. For ages, the big dream for mathematicians was, well, perfection. They wanted to build everything on a foundation that was completely solid. No cracks, no doubts, period.
And the idea was just beautiful, right? You start with a few things that are so simple, so obviously true, that nobody could argue with them. Those are your axioms. From there, using just pure logic, you could build up, well, everything else, the whole shebang.
And this wasn't some new idea. I mean, we're talking way back to Euclid. He built all of geometry on just a handful of these axioms. Jump forward to the early 1900s, and a guy named David Hilbert decided, hey, let's do this for all of math. But then, 1931 happened, and that dream hit a massive wall.
Yeah, a mathematician named Gödel basically dropped a bomb on the whole project. He proved that for any powerful system of rules you create, there will always be true things that you just can't prove using those rules. It was a total game changer. The dream of perfect, provable certainty, it was shattered.
But, mathematicians don't just give up. Gödel's discovery didn't stop the quest. It just changed the question. The new question became, okay, if we can't prove everything with one set of rules, what can we prove? And what specific tools do we need for each job?
And this is where this super cool field called reverse mathematics comes into play. Normally, you start with your rules, your axioms, and see what you can prove. But reverse mathematics flips that script completely. You start with a theorem you already know is true, and you work backwards to figure out the absolute minimum set of rules you must have needed to get there.
Seriously, think of it like being a detective. The theorem is the outcome, and you're the investigator working your way back to find the essential clues, the axioms, that absolutely had to be there for it to happen. Now, this field usually plays around in what's called countable mathematics. So things you can count like integers, 1, 2, 3, and so on, even if they go on forever. And to do this, they use some pretty heavy-duty logical tools.
Okay, so that's the big picture. Now, we're going to zoom in. We're going to sharpen our focus from this big, abstract world of infinite numbers down to something much more concrete, the world of computation.
And this is where the difference really pops. You see, general reverse mathematics, it's often wrestling with these huge, infinite ideas. But bounded reverse mathematics, it's all about the nitty-gritty of computing. It asks a different question. What are the bare minimum rules we need to prove things that matter for computers, where things like time and memory aren't infinite? They're limited or bounded.
So to really nail it down, this is all about finding logical efficiency. We're on a mission to find the absolute weakest assumptions we can get away with to prove important stuff in both math and computing. And if we can do that, we can start to really understand what our computers are truly capable of.
And this is where it gets really cool, because this field, which sounds super abstract and logical, has a direct line to one of the biggest, baddest, most famous unsolved mysteries in all of computer science.
So what's the secret? Well, it all comes down to a special kind of logic called bounded arithmetic. Just think of these as, well, rule books for math that are deliberately weak. They can only think about numbers up to a certain size, kind of like how a real computer has finite memory. And here's the brilliant part. The proofs you can make inside these bounded systems are directly connected to how efficient an algorithm is.
Here's how that bridge works, step by step. First, you prove something using one of these weak, bounded theories. Then, you translate that proof into a different kind of logic. And what pops out at the end? A short, efficient proof. And in the world of computer science, getting a polynomial-sized proof, that's the gold standard. It tells you the problem is actually solvable in a reasonable amount of time.
So, you see the link now, right? The strength of the rules we start with, it's tied directly to the efficiency of our computers. This gives us a whole new way to attack some of the deepest questions about just how hard certain computational problems really are.
Which brings us to the big one, the million-dollar question. Well, literally, there's a million-dollar prize for it. The P versus NP problem, which in a nutshell asks if you can check an answer to a problem really quickly. Does that mean you can also find the answer really quickly?
Now let me be super clear here. Bounded reverse mathematics has not solved P versus NP. Not yet anyway. But what it does do is give us this amazing new set of tools. It lets us ask these bigger meta questions. Questions like, what are the absolute minimum rules we'd need to even begin to prove that P equals NP, or that it doesn't? We're getting a peek at the logical foundations of the problem itself.
Okay, so let's tie this all together. Bounded reverse mathematics isn't just some obscure corner of academia. It's really the next chapter in that ancient quest for certainty, but it's been updated for our modern digital world.
It's this incredible mashup of logic, proof theory, and computer science. And by calibrating the strength of our starting assumptions, we get these really powerful methods for things like making sure the software on your phone or in your car is actually doing what it's supposed to. It's really all about mapping the fundamental limits of what computation can do.
I think this quote just nails it perfectly. It's a modern endeavor to understand the fundamental logical and computational resources necessary to establish significant results. It's not just about proving things, it's about understanding the cost of the proof, both logically and computationally.
And that's really the big idea I want to leave you with. That old dream of a single, perfect foundation for all of math might be gone. But this new quest, the quest for the minimal foundation for any given problem, is turning out to be unbelievably powerful. By figuring out the absolute least we need to assume to prove something is true, we're not just making math more elegant. We might just be forging the very keys that will unlock the next great mysteries of our computational universe.